let's try this example. Now this example looks like it's a different form than before, where we were using the sine theta substitution. This looks more like it's in the form where we're going to use the tan theta substitution, right? When it's in the form a squared plus x squared, we're going to substitute x equals a tan theta, because that allows us then to use the identity tan squared theta plus 1 equals secant squared theta. Okay, so we see this is actually in that form, so we'll try the substitution here. What will be the substitution in this case? We've got x squared plus 4, so that's x squared plus 2 squared. So we're going to do x equals 2 tangent theta. So we'll substitute x here, and then dx. Remember, we also have to substitute dx with the derivative of 2 tan theta, which is 2 secant squared theta. Okay. So we'll insert those values here and here. So x here gets replaced with 2 tan theta, and then dx here gets replaced with 2 secant squared theta d theta. Okay, so we'll have here 2 tan theta squared will be 4 tan squared theta. And then the square root of 4 tan squared theta plus 4. And then dx here becomes 2 secant squared theta. Here, I'll just leave that in the numerator. Okay, so substituting everything in. Now let's simplify what we have a little bit. One thing I could do is I can factor out some constants from the integral. 2 over 4. And I also notice there's a 4 inside the square root that we can factor out, and it'll become 2 on the outside. So we're left with tan squared, and then the square root of tan squared plus 1 here in the bottom. And here's where we want to now use that identity, right? So we see tan squared plus 1 here. Becomes the square root of secant squared, which is really just secant theta. Okay. And here, let's divide out those 2's. So now we got 1 over 4 times the integral of secant squared theta d theta, tan squared theta, and then another secant theta down here. Simplifying this a tiny bit, I noticed the secant squared here. One of those factors of secant will divide with the secant downstairs. So we got secant theta over tan squared theta. Okay, so now how do we deal with this? One thing we could do is we could try and rewrite all this stuff in terms of sine and cosine. So this is oftentimes a helpful way of simplifying a trig expression. Because here I notice that secant, we can write that as 1 over cosine. Tan squared, that's sine over cosine squared. So flipping it over, we'll have cosine squared over sine squared. And then this simplifies a tiny bit. We've got the cosine divides there, and then we've got the sine squared left over in the bottom. Okay, there's 1/4 in front, don't want to forget. Now looking at what we have here, Well, we can do a simple substitution now, because if I let u equal to sine theta, then the derivative will be cosine theta, which we have upstairs. So I'm going to just try that substitution here. Let u equal to sine theta. And du is cosine theta. So here, let me continue in the next line here. So we got 1/4 integral of, now this just becomes 1 over u squared du. Or you can think of it as u to the negative 2 power, right? It makes it a little bit easier to integrate like that. Because now the integral of that will be adding 1 to the power negative u to the negative 1. So I'll write negative 1 over u. Okay. We'll now put the u back in, which was sine theta. All right, negative 1 over 4, 1 over sine theta. Okay. But keep in mind, we also have to return to the original variable x. So let's up here draw our little triangle for the substitution. In this case, we substituted x equals 2 tan theta. So from there we get tan theta equals x over 2. So that'll be the opposite over adjacent side. And then the hypotenuse, we'll use Pythagorean's theorem, will be the square root of x squared plus 4. So from there we can finish it out. The sine of theta will be sine of theta would be opposite over hypotenuse, so 1 over, we'll flip it over, so hypotenuse over adjacent. So hypotenuse over opposite, excuse me. Okay. So there we have it, negative 1/4 times the square root of x squared plus 4 over x. In this next example, it looks kind of similar in that it's got that a squared plus x squared form. But would we need to use trig substitution in this example? Well, if you guys are clever, you notice that we don't actually need to use any fancy substitution. Just a normal substitution would work fine here. And the reason is because when we take u equal to x squared plus 4, the derivative is 2x, which is exactly a multiple of what we have upstairs. So here, just a normal substitution works fine. You could probably work this out using a trig substitution, but it might make it more complicated than it needs to be. So here I'll let u equal to x squared plus 4, and then du will be 2x dx. So I'll have 1/2 du equals x dx. So this integral becomes 1/2 integral of 1 over the square root of u du. This, notice, is just the integral of u to the negative 1/2 power. So the integral of u to the negative 1/2 will be u to the positive 1/2 divided by 1/2, so multiplied by 2. And so this will just be the square root of u, and the u was x squared plus 4. Okay. So notice here this was much simpler than having to use a trig sub. We didn't need to in this case. Let's look at one that involves the secant substitution. All right, now notice this is in the form x squared minus a squared. So we're going to let x equal to a secant theta. And then that allows us to use the identity secant squared theta minus 1 equals tangent squared. So let's work it out. So, okay, well, we've kind of actually written out up here exactly what we're going to substitute, because that's exactly what we see. X equals a secant theta, and then so dx will be a secant theta tangent theta d theta. So let's rewrite the integral now. So we got a secant theta tangent theta d theta in the numerator. Then we got the square root of a squared secant squared theta minus 1. Or sorry, minus a squared. Now I can factor out the a squared. So we'll take the a out from the top. When I factor the a squared out from the square root in the bottom, we get another a on the bottom. Now I have the square root of secant squared theta minus 1 in the bottom. And yeah, so this is now where we get to use that identity. Secant squared theta minus 1 is equal to tangent squared. And so the square root of tangent squared will just be tan. Okay, so these a's divide out, and we've got secant theta tangent theta over tangent theta. The tans divide out. So now I just have to integrate secant theta. And we know that's just ln of secant theta plus tangent theta. And now the final step of going back to the original variable, again I can make myself a little triangle to help me with that. With our substitution x equals a secant theta, we know that secant theta is equal to x over a, which is the same as saying cosine theta is equal to a over x. If that helps, maybe that's easier to remember, that cosine is adjacent over hypotenuse. So the adjacent side is a and the hypotenuse is x. And so this missing side will be the square root of x squared minus a squared, using a little Pythagorean theorem. And then we have for secant theta, we'll have just x over a. And for tangent theta, that's going to be the opposite over adjacent here, so the square root of x squared minus a squared over a. One thing I could also do is combine these together, so you got x plus square root of x squared minus a squared Since I'm dividing the a here, we can split it off into a separate logarithm. And this is just some different constant here. I'll call this C2, for instance. So it'd be ln of x plus the square root of x squared minus a squared. X squared minus a squared. Plus some other C2. If you remember back in the hyperbolic function sections, this maybe looks a little bit familiar, maybe resembling one of the inverse hyperbolic formulas. So in fact, maybe if you look carefully at some of the hyperbolic functions, you might recognize that this also resembles very closely one of the inverse hyperbolic derivatives. And so maybe you can think about how to find the antiderivative using one of those inverse hyperbolic functions. So, anyways, but this is a good example of using the trig substitution.